And the second pulse is a 180-degree pulse. What the 180-degree pulse does is actually explained here, but I will use an analogy saying that the 180-degree pulse is equivalent to telling the bicycle riders to change directions and go back. So now you see you have the same distribution here, but at this moment now they all point to the different directions. They all change their direction. They still go with the same speed. What happens? The fast guys are now the ones behind, and the slow guys are the ones in front. And so if they go with the same speed, they all come back at the same time, which we call after the echo time, at the starting line, but pointing in the different direction. This is what we call an echo. And the echo actually has been discovered by Irvin Hahn in 1949. I mentioned yesterday, Irvin Hahn unfortunately passed away this year, a few months ago. And his pulse sequence, he was just fortunate to discover it. Was ready for discovery, and he was a lucky guy who was able to discover it. And this is how he describes it himself. So you do a 90-degree pulse. It is, you put the magnetization, start the magnetization components. First you have Z magnetization. You do a 90-degree pulse along the x-axis, so you flip the magnetization over, right-hand rule, thumb points in the direction of your B1 field, and then you flip by 90 degrees, puts the magnetization along the x direction. And then the magnetization in the rotating frames, some move faster than you, some move slower than you, go right and left, so they spread around. Now we go from 1, 2, 3. This is the next one here. So the magnetization spreads in one way and the other way. I identified two components in color. And then you do a 180-degree pulse along the x direction. The 180-degree pulse means you rotate the whole plate of magnetization components by 180 degrees, which means you exchange red and blue, for example. So that one moves over here, and the blue one moves over here. So 180-degree pulse. And now you have this scenario. But the precession direction stays the same. It's slightly different from what I explained with the bicycle riders. The precession direction stays the same, but still, then after this, after a time, the same time it has taken for the magnetization components to run apart, they assemble back along the x direction. And that gives the echo.
So normally, after 90 degrees, we put in y direction. Is there any particular reason?
Yes, there is a particular reason, because it's better in terms of phase and pulse errors that you get. So it's actually, the better explanation is, actually I've done that too. I have a 90-degree y and a 180-degree x. So there's this 90-degree phase shift between the two pulses. You also can do 90 x, 180-degree x, and the echo forms along a different axis. But phase errors accumulate slightly different. There's compensation schemes for not being able to produce exactly 180-degree, 90-degree pulses, and to compensate those, we play with the phases of these pulses. Yes. And there's the second form of an echo that is still used, and we need that later on when we discuss diffusion, for example, is the stimulated echo, that you can break that 180-degree pulse into two 90-degree pulses and have some time in between. And that is what we call a stimulated echo. It first generates a Hahn echo with two 90-degree pulses. Actually, I should mention that the Hahn echo does not require a 90 and a 180-degree pulse. Irvin Hahn used arbitrary pulses and discovered the echo. He didn't even know at that time how to set a 90-degree pulse properly. And so those pulses, any two pulses, radio frequency pulses, strong enough though, will produce an echo. And the same applies for optical echoes, which also Irvin Hahn discovered, and that you use two laser pulses in a nonlinear medium, and then you generate an optical echo, and you use that for information storage. Now that's a fundamental discovery of an echo, and it's the basics of MRI. No magnetic resonance imaging method would work unless you use this type of an echo. So this is, has a tremendous impact onto modern society that we have these echoes. So this stimulated echo is another one which allows you here to introduce a waiting time of time t1 to then see two echoes, actually, the Hahn echo and the stimulated echo. We see how far we get. Let me do, before we take the break, address just the multiple echoes. And the multiple echoes are the case that you do a 90, 180 degree pulse, you generate your first echo, and then you add further 180 degree pulses and you generate more echoes. It gives you an echo train. There were 4 people, Carl, Marcel, May, Gill, who invented that or discovered that and optimized that. This is why it's called the CPMG echo train. So CPMG is something that many people that measure relaxation know, and especially people in the oil industry deal with it from every day. This is their way of measuring NMR signals. Because the fact is that the echo peaks, the echo amplitudes, if you connect them, they give you the relaxation decay which you naturally observe in perfectly homogeneous fields. And this tells us that in inhomogeneous fields we can still measure that relaxation decay with a simple CPMG multi-echo sequence. Very fundamental for relaxation studies, for materials analysis, for the physics sort of community of magnetic resonance. The chemistry people is not so important. They want to measure the free induction decay, homogeneous fields, get the spectrum. So we will deal with T1 after the break, and then we deal with spin-spin interactions. Okay? Let's take a break. Yeah, questions, of course.
So we have a signal in time domain.
Yes.
So we convert firstly into frequency domain.
We can say again.
Convert it into frequency domain.
Yeah, by the Fourier
Yeah,
transformation.
by the Fourier transformation. We get 2 frequency, one is negative and another is positive frequency.
Yes.
So negative frequency is useful in NMR or just related to phasor?
Well, it's a matter of the spectral width and the way you set your filter in the electronics. It's better to sit actually in the